Hello, and welcome to lesson 12 of this Introduction to Linear Algebra with Wolfram U. The topic for this lesson is determinants. So let's begin with a brief overview of the lesson. So you were introduced to the determinant for the case of 2 by 2 matrices during the lesson on inverses. So let's say your matrix A over here, it's 2 by 2. The first row is 2, 3, the next row is 6, 13. And if you work out its determinant, the answer is 8. And that's because if you multiply the elements, so the diagonal elements, you get 2 times 13 is 26, and then 3 times 6 is 18, and if you subtract them, you get back the answer 8. And the point is that a 2 by 2 matrix is invertible if and only if its determinant is non-zero. So in this lesson, we'll talk about the determinant in the case of n by n matrices where n could be some large number. And as we just saw, the determinant function, the det function, can be used to compute determinant for matrices of any size, not just 2 by 2. So for example, here is a 3 by 3 matrix, and you can work out its determinant. And the answer is 22. Now these determinants have got many applications. So for example, they can be used to solve linear systems, and hence they are quite important in linear algebra. Okay, so let's begin with a general definition of determinants. So let's say you have a square matrix and all our matrices are square over here, and the ijth element of the matrix is small aij's. What you can do then is to delete the ith row and the jth column of A and get another submatrix aij. So aij over here is smaller than the original matrix A. And in this case, the determinant is given by an alternating sum, which means that alternately got plus and minus signs over here. So let's say we have A11 times determinant of capital A11 minus A12 times determinant of capital A12, etc. So you got plus minus, and that's the definition of the determinant. But you'll notice that this is actually a recursive definition, because to compute these determinants over here, you need to work with smaller matrices, so you've got to go all the way down until you're done. Okay, so as an example, let's take a 3 by 3 matrix A. And if you look at the first row over here, 10, 6, 4, then let's call that as A11, A12, A13. Now, once you've done that, then you begin by deleting the row and column as required. So let's say if you look at the element 10 over here, you need to delete the first row and the first column, so you get the submatrix capital A11, which is 7, 1, and 5, 3. Then you can take the element 6 and delete its row and column, and you get the submatrix 1, 1, 4, 3. And then you can do the same thing with 4 over here, and you get the submatrix 1, 7, 4, 5. And hence, the determinant over here is going to be the elements of the row times the corresponding determinants of submatrices. And if you do that over here, then you get back the answer as 74, and you can check the answer with det to get back just the same number. Now, let's take a slightly larger example with a 4 by 4 matrix over here. So now you have 4 elements in the first row. They are 20, 1, 19, and 17. Now you can work out the corresponding submatrices. So the first submatrix over here, A11, for example, is going to be 11, 22, 3, 18, 16, and 12, 2, 4. And then you can work out the remaining 3 as well. So for example, the fourth submatrix over here is obtained by deleting the first row and the fourth column. So you get 14, 11, 20, 1, 3, 18, and 15, 12, 2, like you see over here. And then you can apply a definition to work out the alternating sum, and you get back an answer which is quite large over here, but you can check it with det, and you get back just the same answer. Now the point is that there are many simpler matrices for which you have determinants which are quite easy to remember. So for example, if you have the identity matrix of order n, then its determinant is always 1. So for example, here is the identity matrix of order 3. So it's got diagonal elements 1, all of the elements 0. And if you try and expand it, then in the first row you only have one non-zero element. And if you look at the corresponding submatrix, then you simply get back a smaller identity matrix. So you get this submatrix over here, and hence the complete determinant is just 1 times 1, which is 1. So the point is that if you have such a matrix, the determinant is always going to be 1. Let's check the answer with the built-in function, and you do get back 1 over here. Okay, another simple case is the case where you have a diagonal matrix. And in such a case, the determinant is going to be the product of the diagonal elements. That's a nice result. So for example, here you have a diagonal matrix of order 3. The elements over here are 3, 4, 5 along the diagonal. And again, if you try and expand it out, in the first row you only have one non-zero element 3. Work out the corresponding submatrix. And hence, if you go recursively, the answer for the determinant is going to be 60, which you can confirm quickly. And as another simple case, let's talk about a lower triangular matrix. So once again, in this case, we'll find that for a lower triangular matrix, the determinant is going to be the product of the entries on the main diagonal. And that's because when you try and expand out, it's only the leftmost entry at every stage which is non-zero. So for example, here is a lower triangular matrix. You see over here you only have non-zero entries below the diagonal. And if you try and expand out with the first row, then the only non-zero element is 2 over here. Then you get a smaller sub-matrix, which itself has got a simple structure. It's lower triangular. So in the end, you simply do 2 times 5 times 7, you get 70, and you get the same answer from the built-in function det. Okay, now the question is, how about an upper triangular matrix? But to do that, we need a slightly different idea, and that's the cofactor expansion. So here's another way of finding determinants. So let's say you have a square matrix again, capital A, and the ijth element is small aij. Then you do the same thing as before. You work out the submatrix, capital Aij, by deleting the ith row and jth column. But now you define the corresponding cofactor to be not just the submatrix, but also the submatrix determinant times the factor over here, which is minus 1 raised to I plus j. So basically what you do is you kind of try and build in the negative factor into the calculations. Once you do that, you get a much simpler form for doing the determinant. But the main point is that now you can use any row or column to the expansion. So this method over here is going to work for any row or column expansion. And the way to determine the signs over here is for the first row you got plus minus like before. Second row you got minus plus minus, etc. So the signs kind of alternate, and you can use this matrix to determine what to do. Okay, so as an example, here is a matrix A. It's 3 by 3. I want to expand it using the second row. Now, second row is 1, 5, 6, like you can see over here. So you work out the corresponding cofactors, which are 2 by 2 determinants with the correct sign. So you got minus, plus, and minus over here with the second row. Then you work out the determinant. And once you've done that, you can check the answer is 135. So the point is, with the cofactor expansion, you can use any row or any column. And that's the key idea for finding the determinant of an upper triangular matrix. So for an upper triangular matrix, we'll find that the determinant is again the product of the entries on the main diagonal of A. And that's because now if you expand with the first column, then it's only the topmost entry, not the leftmost, but the topmost, which is non-zero. So for example, here is an upper triangular matrix A. You expand using the first column, and you get 3 times determinant of 5, 1, 0, 4. And if you do that recursively, then you get back the answer 60, which you can confirm with the built-in function det. Okay, so that brings me to the end of the lesson, and the point is that in this lesson we've only spoken about the definition and calculation of determinants. And there are two ways to do it. You can either use a recursive formula with the first row, or you can use a cofactor expansion. Of course, they're related. And the second one is much more general. And then using these ideas, we worked out simple formulae for determinants of identity matrices, diagonal matrices, and triangular matrices. And having done this, in the next lesson we'll talk about the properties of determinants. But before doing that, do review this lesson. It's rather simple, but quite important. But let's stop over here. Thank you very much.